Hello again. This is Mr. Simpson, and I'm going to work through this, at least some of this final review, along with you. There's already a written out version of my answers to this review, and so what I'm going to do is look at some of the ones, either just say a quick word about them, or work through some of the ones that I think you might need a little bit more help with. Okay, so let's start with this first part. Now, of course, you know that when you're doing f of anything, whatever's in those parentheses, all you do is plug it in for x. And then simplify. Same thing here. No matter what's in these parentheses, everywhere there's an x in the formula, just plug in whatever's in that set of parentheses. In this case, it's a 2 plus h. And then simplify. And you can see the simplification on the written solutions here. So a couple of things we want to remember. This is the domain. So remember, the domain is all of the x values that you actually can plug into this function and get an answer. So how would you not get an answer, you ask? Well, let's say you've got a square root, and underneath this square root you have a negative value. Now, this will give you an answer, but not a real answer. So, what x values can you plug in so that this does not happen? You want to get either a positive value or 0, a non-negative value. Or in other words, the x minus 2, whatever's underneath the square root, has to be greater than or equal to 0. It's got to be positive or 0. At least it can't be negative. So, what x values would make that work? Well, a real simple way to do this is just add the 2 to the other side, and you know that x has to be greater than or equal to 2. Or in interval notation, that's everything from 2 up to infinity. So starting at 2, including 2, that's why it's a square bracket, all the way up to infinity. And remember, you never include infinity because it's not actually a number. Okay. Oh yeah, this one. So what bad thing can happen in a fraction? Well, you could have a 0 on the bottom of the fraction. That would be a problem because you can't divide by 0. So what x value would you plug in that would give you a 0? Well, that would be 3. So basically what you have here, x can't equal 3. Now, how do I write that in interval notation? To help me out, I'm going to draw a little number line. So here's 3. I know I don't have 3, but anything else is fine. I can plug in 4 or 2 or 2.999, but it still won't give me a 0 on the bottom. So it's everything except 3. Everything to the left of 3, everything to the right of 3. So I have 2 different intervals of numbers here. This interval would be everything from negative infinity up to, but not including 3. Or I can have 3, but not including 3, all the way up to infinity. So this is everything less than 3. This is everything greater than 3. We've come in with our scissors and snipped out just the value of 3. Everything else is fine. Okay. You want to be able to know the basic shape of these parent functions, some that we've talked about through the year. Hopefully by now, since we've done this for every single function that we've talked about, you know what these transformations are. So if you're describing it, you would want to say something like, this goes to the left 3. This goes up 3. So be specific there. Remember, anything that's inside the parentheses affects the x's and does the opposite of what it says. Anything that's outside the parentheses affects the y values, and it does what it says. So this would be left 3, up 3, a vertical stretch by 3, a horizontal shrink by 3, and a negative is going to give you a reflection because it's outside. It's going to flip the y values. So it would be either an x-axis reflection, it's across the x-axis, or you could say a vertical reflection. But x-axis reflection would be the best way to say that. How do you solve for an inverse? Well, you switch the x and the y. And then you solve for y again. And again, let's see, first you would multiply by 7, then add 3. there's the inverse. We've done that for lots of different kinds of functions. Okay, so this part that might not come into your memory quite as easily is the polynomials and rational stuff. So here we need to factor. One of the main things we do with polynomials and rationals is look for zeros, and similarly look for asymptotes. So to find zeros, one way is to factor. So let's try to factor this. Now, the first thing you should do anytime you're factoring is look for common factors that are in each term. So if you look at the numbers, I can factor out a 2. If you look at the x's, I can factor out an x squared. That would be the least number of x's that show up in any of these. So I can take at least 2 x's out of all of these. Now, what's going to be left over? So remember, essentially when you factor something out, you're dividing each term by that value. So what would I get if I divided 2x to the 4th by 2x squared? I would get x squared. Here, the 8 and the 2 would give me a 4, and x cubed divided by x squared would just be 1x. And here, I've got a minus, and then that would be 21, and all the x's are gone, like so. So 2x squared is one of my factors. Now, we've got an x squared polynomial left over on the inside. That means we're going to have 2 factors that come from here. So besides the 2x squared, which we don't want to forget about, we're going to try and factor this. Will it factor? If not, you could also use the quadratic formula to get the zeros. But let's try to factor it first. So when I have a 1 as my leading coefficient, that makes the factoring a lot easier. I just need 2 numbers that multiply to get negative 21. That means they're going to have opposite signs. And they add to get 4. And of course, since they have opposite signs, they really subtract to get 4. So how about 7 and negative 3? Would that work? Let's see. X times x is x squared. Negative 3x plus 7x would give you 4x minus 21. Hey, it works. Now I set each factor equal to 0 to find the zeros. So either 2x squared equals 0, or x plus 7 equals 0, or even x minus 3 could equal 0. So any of these will be a 0. So for the first one, x would just equal 0. For the second one, we get x equals negative 7, and for the last one, x equals 3. So there are my answers, and of course you could also write it like this. X is negative 7, 0, and 3. Okay. Next. So for 25, sorry, for number 7. Not sure why I said that. Okay, for number 7. So we're told that x minus 4 is a factor of this polynomial. We want to show that using synthetic division. So let me remind you how to do that. First, I'm going to set it up. Okay. Now, from this polynomial, I just use the coefficients, the number parts. So if there's not a number, of course, that's a 1. So 1x cubed plus 4x squared minus, so I need to keep the minus, 25, and then minus 28. Now, the number that goes in here when I'm doing synthetic division would be the 0 from this factor. So if x minus 4 is a factor, that means that x, my 0 from that factor, would be a positive 4. So I'm going to put that there. Now, my first step, I'm going to take this 1 and drop it. Now I'm going to multiply. 4 times 1 is 4. Now I'm going to add. 4 plus 4 is 8. Now I'm going to multiply. 4 times 8 is 32. Now I'm going to add. Negative 25 plus 32 is 7. Now I'm going to multiply. 4 times 7 is 28. Now I'm going to add. Negative 28 plus 28 is 0. Is that good or bad? Well, this is what we wanted. This is how we know that this x minus 4 actually is a factor, or equivalently, that 4 actually is a 0 of this polynomial. So I'll put a little smiley face. That's what we wanted. We wanted a 0. Okay, so that means not only is x minus 4 a factor, but we just factored it out. That's why we like to do synthetic division for this kind of thing. So we have simultaneously shown that 4 is a 0, and also we have factored out this x minus 4, what's left over. So what you do here is you bring the original exponents down by 1. So instead of leading with x cubed, you're going to lead with x squared. So that's 1x squared, just x squared. And then this would be x to the first power, so 8x, and this would be 7 with no x's, like so. So here are my factors. And now I need to take this trinomial here and see if I can break it up into 2 binomial factors. Or if I can't, then I can use the quadratic formula. But I can. So again, I've got a 1 as my leading coefficient. So I know my first 2 terms are going to be x and x, and my last 2 need to multiply to get 7 and add to get 8. For instance, they could be positive 7 and positive 1. And if I FOIL these 2 things back together, I should get what I started with. And I do. So what are my x values? I'm going to set each of these equal to 0. These would be the zeros. That means set it equal to 0. And so I get 4, negative 7, and negative 1. Alright, let's look at the back. Okay, so I mentioned, well, I'm mentioning now, there is a typo here, and so this should say a triple asymptote. So what we want to remember here is that zeros, or roots, go on the top, and asymptotes go on the bottom. And a whole goes on both the top and the bottom, so it would cancel out. So it's neither. Okay, so we've got a single root at 5. So what factor would give me a root or a 0 at 5? Well, x minus 5 would. And it's single, that's telling you the exponent. So x minus 5 to the first. There's one copy of that factor. And we have a double root at 0. What factor would give me a root at 0? X would. So x minus 0, if you want to think about it like that. But it's a double root, so we're going to square it. And we've got a triple asymptote at negative 2. So first off, it's an asymptote. That means it's going to go on the bottom, not the top. It's tripled. That means it's got an exponent of 3. Or in other words, there are 3 copies of that factor. And it's at negative 2. So the factor would be x plus 2. And then we've got a whole at 1. So that factor would be x minus 1. But because it's a whole, it cancels out. It's going to be on the top and the bottom. Okay. Now it's time to play cross or bounce. So we want to factor, we want to graph this factored polynomial. It's already factored for you. So that makes it really easy to find where the zeros are. And remember, the zeros on the graph are the x-intercepts. So zeros, roots, x-intercepts, they all mean the same thing. So if I look at the factors, that tells me immediately what the zeros are. So I'm going to have an x-intercept at 0. I'm going to have an x-intercept at 1. And I'm going to have an x-intercept at negative 3. So before we draw on the graph, there are a couple of things we need to decide. First off, what sort of behavior is going to happen at each of these zeros? So the x-intercept at 0 came from this x squared factor. The exponent tells me what sort of behavior is going to happen. So in this little area around the x-intercept, we're going to see something that looks similar to the function x squared, which is a parabola. So what I'm looking for, is that going to cross or bounce? Well, a parabola would bounce there. So I'm going to put a B, bounce. What would happen at 1? Well, this is raised to the first power, so in that little area around this 0, it's going to look similar to a linear function. So it's going to cross. And it's going to go straight across. And for the last one, where we have an x-intercept of negative 3, that's from the x plus 3 factor, and it's raised to the third. What does x cubed look like? Well, that's the one that crosses, but it squiggles. So I'm going to put an SC for squiggle cross. Okay, now we know what's going to happen. We just need a place to start. Are we going to start up here, or are we going to start down here? And to answer that, we actually want to think about this question number 10. What's the degree of the polynomial? So if I add up all of the exponents on the factors, a 2 plus a 1 plus a 3, it's got a 6th degree. So x to the 6th is going to look similar because it's even. It's got that even symmetry, so y-axis symmetry. So it's going to both start and end up in this case. Or if one of these factors was negative, it would both start and end down. So it's going to start up and end up. Some other stuff's going to happen in between, but we're just looking for, first, for the end behavior. So up and up. That's our end behavior. The degree is just 6. So the end behavior, we're going to start up. Now, what am I going to do when I get to the 0 of negative 3? Well, I know from previous work that I'm going to squiggle across. So there's my squiggle, something like that. What's going to happen when I get to 0? I know I'm going to bounce. Boop. And then for the next one, I'm just going to go straight across. And that's the basic shape of the function. That's what we're looking for here. So we know where the zeros are. From this picture, we know where the function is positive and where it's negative. We know about where the minimums would be and the maximums, minima and maxima. So all that we can get just from drawing this neat little picture of the function. And if we want to investigate further from there, we know where to look. Okay, last section, logarithms. Yay. So, for these first two, all we want to do is try and rewrite this as either an exponential or a logarithmic equation. So we want to switch back and forth from one to the other, essentially. So one thing you might or might not remember is drawing this little heart. Okay, or maybe some more clever way that your Algebra 2 teacher taught you how to remember this. So when we start writing this, first we're going to use the base and the exponential as the base on our logarithm. So log is going to have a base of e. And then the thing inside the logarithm is going to be the next thing. So log base e of t equals 7. So this heart tells you in what order you should write these things down. Now, we don't write log base e. That's the natural log. So be sure and write it that way. If you don't, I'm going to count off points. This is the correct way to write a natural logarithm. You need to know what it looks like. Then let's try the same thing for part A. So again, we're going to write the things in this order. We're going to start with a 2, then a 20, then a y. So 2 is going to be the base. It's the base of our exponential. It's also going to be the base of our logarithm. Log base 2 of 20 equals y. And you don't have to put these parentheses. Those are optional. I'm just trying to add them for clarity. Log base 2 of 20 equals y. Now, we can do the same thing for a logarithm, trying to write it as an exponential equation. The base of the logarithm is going to be the base of our exponential equation. And we can use the same heart shape to figure out what order stuff goes in. So 3 raised to the 7th equals x. And on this one, we don't have a base written. That means the base is 10. This is log base 10, a standard logarithm. So 10 is going to be the base of my exponential. The exponent is going to be w, and that equals 9. 10 to the w equals 9. So again, the heart tells you what order to write those things down in. Okay, so recall that logarithms and bases are inverses of each other. That means when they have the same base, they can cancel each other out. So logs, exponentials are inverses when they have the same base. And inverses cancel each other out. So let's look at A. we've got an exponential with a base of e. And what's the base on the natural log? Oh yeah, it's also e. So the exponential and the logarithm cancel each other out, and what's left over is just this x. Here, we've got a log base 7 and an exponential with a base of 7. Those are inverses. They cancel each other out. And what's left over? A 3. Log base 2 of 32. Now, this one's not immediately obvious unless you remember that 32 is 2 to the 5th. So the log base 2 and the exponential with a base of 2 are inverses. They cancel each other out. What's left behind? 5. Okay. Number 14. So here we want to solve this equation by making the bases on each side match. Now, this is a base of 9. This is a base of 243. Can I write 243 as 9 raised to some power? Let's see. 9 squared is 81. 9 to the third would be 9 times 81, 729. So no, we already blew past 243. But maybe there's some other number I could use as a common base. What about 3? I know that 9 is 3 squared. What about 243? Let's see, 3 squared is 9, to the third is 27, to the fourth would be 81, to the fifth would be 243. So that's 3 to the 5th raised to the x power. Now, when you have an exponent raised to another exponent, those two exponents get multiplied together. So I'm going to get 3, and then I'm going to do 2 times x plus 12. And remember, you would distribute there. 2x plus 24 equals 3 to the, so 5 times x is just 5x. Since the bases match on each side and these two expressions are equal, that must mean the exponents match as well. So 2x plus 24 equals 5x. Subtract the 2x over, you get 24 equals 3x. Divide by 3, x equals 8. So cancel out the bases and just solve this equation right here. Set the exponents equal to each other. Subtract the 2x, divide by 3. And one last exponent, exponential. To solve this, we're going to use a logarithm. So oftentimes when solving equations, well always when solving equations, we use inverses. For instance, I notice that this 2 is multiplied by the e to the x. What's the inverse of that? Dividing by 2. So the first thing I'm going to do is get this exponential equation isolated. Okay, I've got the exponential part isolated. Now to cancel it out, just like we do with, say, a sign or multiplication or addition or subtraction, to cancel this e out, we use its inverse, which would be a logarithm that also has a base of e, also known as a natural log. So we're going to do the natural log of both sides. Those cancel and leave behind x, as previously shown. So x equals the natural log of 5. Now, what is the natural log of 5? You can ask your calculator. I don't have mine, but I think it's 1.6-ish. Something like that. If I'm wrong, it's on the written solutions. Okay, so that's it for stuff from the first semester. Again, if you have any other questions beyond what I've covered, you know where to find me. Trig Test 4, which is the one I'm letting you correct and turn back in for half credit, if you would like to, is your review for the trigonometry part of the final. Anything that's on there is fair game. Even if I didn't grade the question, be sure and look over all of them and correct all of them. And then sequences and series. So we took, or are taking, depending on when you watch this, a sequences and series quiz in class. I'm going to let you keep that and use that as your review for the final. So all that stuff will be covered. And again, if you have any questions, I'm in room D209. I'm there every morning, every afternoon. I'm there during class. Come find me. All right, have a good day.